I moved the deadline for the homework back to Saturday at midnight. I'm sure you're welcome. So there was a mistake where I had something from last semester got propagated forward that said Saturday the 7th at midnight. There's no Saturday the 7th this year, so I want it to be done before you take the midterm, which is Monday. So I put it on Saturday night. So I think it's reasonable. So hopefully now you have enough time to finish the homework if you haven't already. I know a lot of you have turned it in already, which is great. All right. So any questions on the homework or the midterm? Yet? So, okay. So we'll get into the topic of the lecture, which is the singular value decomposition. And so this is kind of a very powerful tool from linear algebra that turns out to really be at the core of what's going on in a lot of techniques that show up in data mining, from dimensionality reduction to things called principal component analysis, to eigenvalue decomposition we talked about before, to multidimensional scaling, and these are all related. So what we're going to talk about today is basically so we're going to start with basically review of the SVD. I'm not sure if it's taught in the linear algebra class here. I think it probably should be if it's not, but it may be taught there. We're going to review the SVD and all the linear algebra that goes into it. So trying to give some, we're going to try and give some geometric intuition about how to think about the singular value decomposition. So it turns out when you're using this for data mining, there are lots of places where it comes up, but a lot of the different places are use this in a way that's different, depending on the setup, depending on how you think about your data. And so if you just know to blindly apply it in one case, you may not understand its full power. So I'm going to kind of allow you to kind of get different views of this decomposition, so that you'll be more comfortable trying it out in more than just the standard way of doing it. So hopefully that helps. And then we'll talk about the connections to PCA, which is principal component analysis, to the eigen decomposition, which we talked about with spectral clustering, and will come up again in the PageRank, and then into multidimensional scaling, which maybe you've heard of. Some of these terms are defined differently in different contexts and different textbooks, and they often mean roughly the same thing, but sometimes slightly different. And I'll give what I think is the most standard way of viewing them, or at least the most logical way to think about them. Okay, and that's what we'll use in this class, but you might see them defined slightly differently elsewhere for kind of various reasons. Okay, so what we're going to be thinking about is our data. Our data is going to be a matrix. Okay, and I'll write this matrix as A here, and it's going to have these D columns, and it's going to have N of these rows. Okay, and so now we'll think of every individual, each row is going to be one data point. Okay, each row is going to be one data point, and then if I have a column, right, so this column going in here, this is one attribute. of the data point, or you can think of it as one coordinate. All right, so another way to think about this is that we have these data points AI and A, and each is going to be some data point in RD. So it's going to be in this d-dimensional Euclidean space. The green's not working. Good. You kind of see it up. Okay. Anyways, well, best not to try and fight it. Okay. All right, so let's try this again. So one column. That looks just like the purple, huh? All right. Let's try. The blue kind of looks, okay? That looks different than the purple. All right, so let's try that. So this is one attribute of the data, or so one coordinate. And so then for each AI and AI is going to be in RD. So we're going to think about these as high-dimensional points. Each of these rows, so this is going to be row AI. This is going to be a high-dimensional point. Okay, and so then if you think of it this way, what the goal is going to ultimately be to find a way, this D is going to, N is going to be big, D is going to be big. We want something, a smaller set of dimensions, which is going to work nearly as well as these. So often we want this to be in like 2 or 3 dimensions so we can actually see what's going on. We can plot them, right? So even D equals 10, it's hard to visualize what's going on. So going down to 2 or 3 would be helpful. We'll give some different examples of this as well. Okay, and so more specifically, what the ultimate kind of goal is going to be to find a mapping from RD to RK, and this mapping is going to be this mu mapping, and actually the specific RK here, I'm going to think of this as lying in a subspace of RD. So this is a little weird to write it this way, but and you want to minimize the sum of AI and A of AI minus. Okay, so for I want to sum over all of the data points from every data point which lives in a high-dimensional space to a low-dimensional subspace. So I'm mapping to a lower-dimensional space here. Think of K as maybe 2 or 3. And I want to do it so that the sum of the squared distances of all these movements of the points to this lower-dimensional subspace is minimized. Okay, good.
So I'm a little disturbed by how this is being defined because
okay. Yeah, all right. So let me. It's good to have a mathematician in the room. So let's define this to a subspace F, and we'll say that. So it's going to map from RD to subspace F, and we'll say that F is a k-dimensional so subspace. Okay, is it so this is a little better?
Yeah, a little bit. So basically you're filling in zeros everywhere else.
Not really. So it's not. We'll see it. We're not. it doesn't need to, I mean, it fills in zeros in a certain rotation of the parameter space.
Okay. But
So,
yeah,
I'll define this more clearly, but this is kind of it. So maybe I'll try and draw a picture. So we're going to think of these points and pretend that, so we'll first start with d equals 2, and then I can draw this subspace here as f. Now f is now a one-dimensional subspace, and I want to find this subspace such that if I look at all of these projections, which you can't really see, but I'll draw a lot of them so you don't want to declutter anyways. Right? If I draw all of these and I sum their square distances, right, then I want to minimize the choice of this one-dimensional subspace, right? So it's a smaller dimension. Now, if D was 100 and this was 2 or 3 dimensions, this kind of works again, right? And in fact, we're going to define an orthogonal Euclidean basis that lives inside of F as well. So it's actually going to look like RK exactly. We're going to define this basis, and we can give everything coordinates in this new k-dimensional Euclidean subspace, right? So it's I know I felt okay. Yeah. All right. So let's so it's very cool how this all works if you haven't seen it before. All right. So this is the ultimate goal of what we're going to be doing, and it turns out that there's this very old linear algebra tool that will give us exactly this, and we'll define it more precisely. And so we're gonna start by, let me draw this. We're going to start with this matrix A. Right, this matrix A again, and the singular value decomposition is going to be writing this as a product of 3 matrices. So we're going to be A is going to be equal to U times S times V transpose. And typically, if you call this in MATLAB, which I'm going to ask you to do on the homework and so forth, you would do SVD of A. You can probably do this in other languages other than MATLAB. Octave is open source and free, and you can use that instead. We're going to the product of these 3 matrices, and they're going to look something like this. So the first one, U, is going to be a big, right. Let's try this one. U is going to be this big old square matrix. It's going to be n by n. You're going to have, try this one. Nope, didn't see that one at all. All right. Okay. S is going to be n by d again. This is going to be S, but it's going to have the property that it's all zeros except for along this diagonal. All right. So when I'm drawing these boxes, you're not familiar with this kind of way of doing it. Think of it as a matrix. There's actually a bunch of, you can think of like a grid in there and there are all these elements in there. And so then the last part is going to be V transpose. So yeah, S was n by d, and then V transpose is d by d. Okay? So the singular value decomposition is going to give you this. So you're taking a matrix which often is already big and you're making it even bigger. But these are going to tell you a lot of cool stuff about A. So let's talk about these now. So U and V are going to be these orthogonal matrices. So that means that what they're doing, what you can think of doing, and I'll draw some pictures to help you imagine this a little bit better, is they're kind of rotating the space. They're changing the coordinate system of the space. And I'll describe what that means in this context a bit more. So that's going to mean a few things. So each column of U and V, so the row of V transpose is the column of V, is going to have, so for instance, UI is always going to be equal to 1. So what this means is that this is not changing the scaling of anything. Every time you multiply by any of the columns, it's not going to change any of the scaling. And that for each pair, so for a pair of the columns, UI and UJ, we're going to have that UI UJ is going to be equal to 0. So what does it mean if the dot product of two vectors is equal to 0? It means they're orthogonal to each other, yes. So they're gonna need to have these right angles here. This is UI, this is UJ. So it means that, so just like the x-axis and the y-axis are orthogonal to each other, these are going to be orthogonal to each other, but they're usually not going to be exactly the same x and y axis. There's going to be a different set of axes that are rotation of the original ones. Okay, and also it's going to be that the transpose is the inverse. So V transpose is going to equal to V inverse. This implies that V transpose V is going to be equal to the identity matrix. So that means if you multiply by V and then V transpose next to each other in kind of a string of products, those are going to cancel each other out. So, and we'll see this when we talk about relating this to the eigendecomposition. This is going to allow us to understand this. Okay. All right, so those are the orthogonal matrices, and that doesn't really tell you that much yet. What's more interesting is when you start looking at this, let me go to here and I'll come back. All right, so S is going to be a diagonal matrix, as I said, and so we'll write these S1, S2 up to SR, where R is less than or equal to D is actually up to then. So R is less than or equal to D, and this is what's called the rank. Okay, so what's going to happen is these values are going to go, so this is going to be SI. So the ith one in there is going to be the ith entry on this diagonal, and everything else is zeros in there except for these on this diagonal. And we're going to have that SI is greater or equal to SI plus 1. Right? So there's an ordering. These are decreasing. Okay? Okay, so now what's kind of illustrative is to, let's see if I can draw this effectively without messing too much stuff up. So this part of this matrix, and this is a good use of the colors you can't really see, this matrix, this part is all zeros. And so when you multiply this by U, that means that this part here is multiplied by all zeros. So this, move this down a little bit. Yeah. All right, so this part of U doesn't do anything. So we can ignore this part of U. Now, it has structure, so U is an orthogonal matrix. It completes some basis, but this part of it doesn't matter at all because this is all zeros. Sometimes when you see this written, you'll see S written as a square matrix, just the diagonal upper part. But then you can't really product them together in a way that makes sense. Okay? And then if the rank is less than D, right? So now if some of these other ones here are also 0, right? If these are also 0, then this part also doesn't matter. And that means that this part also is not important. Okay? And this bottom part of V is also not important. Okay, so if there are more zeros here, if the rank stops there, then this part's not important, and that part you can ignore as well. Okay? And so typically what you do, when you look at this, you're going to pick some value sk and say, this is the last one I care about, and then I'm going to make these all zeros. Okay, so there may be some other stuff here, but these are decreasing. These are getting smaller and smaller. And in a lot of data sets, these tend to be really close to zero. This is kind of the noisy part of the data in some way. So you just snap all of these to zero here. So you reduce the rank, and so that means that if you go back up to our matrix, you set more of these things to zero. This is up to sk. Okay, and so now this becomes zero as well. And so now you trim off even more of this. Right, and this one gets trimmed. And so what you have left now, afterwards, you're going to get this matrix will be called UK. This is an n by k matrix. The top part here is called sk, and this is going to be a k times d matrix, and this top part is vk transpose, which is also going to be, did I do that wrong? Yeah, that's still fine. It's, yeah, the reason you chop off the bottom ones then kind of it's because there's also these these blocks here that you also don't care about here. Right, so that's why the bottom part doesn't matter as it turns out. Okay, so then this is going to be, this top part here, VK transpose, is going to be a K by D matrix here. Okay? Right? Okay, so now let's look at what's left here. I'm not sure I got these. Okay, so now we're going to get our A matrix. We're going to call this now A sub k, which is n by d. And this is going to be equal to U, which is n by k. Make sure I get I think I want to pad some stuff with zeros here. This is sk. Let me draw these and make sure I get this right. And this is V transpose k. This one you want the rows of here. So this is going to be k times d. Yeah, so then you can make this a k by k matrix. Yeah, make sk by k. So you shrink it. So yeah, so you just keep the upper k by k part in this case. Okay, so this is k by k. All right. So now this is called UK. So now this is what's called AK. Now this is still, it's an n by d matrix again. All right. This is UK, SK, and VK, which are now these smaller parts that you care about. But what you know, and I'll kind of walk you through the mathematics of this now, that now each of these data points now, so these are A1, let's call them bar. So for all A1 bar, these are going to live in some subspace F. And the subspace F, F is going to be so k-dimensional, and it's going to be a subset of RD. all right? Because this is still going to have d coordinates to it. This still has d coordinates. It's an n by d matrix. So, so this has d coordinates, but it's going to turn out it's going to live in this subspace F, which is going to be k-dimensional. So this gives me a subspace. It turns out that these data points are going to be this projection that I want to define. Okay, so I'm going to have this mu of AI is going to equal AI bar that I get out of this, where based on however I set this parameter k. Right, so this is going to give me this picture here where F is this subspace, and I projected all the data points onto here. And this is going to be the one that's minimizing the sum of these squared pairs. Okay, so this is kind of the magic of what's going on here, and we'll walk through this a little bit more now. But right, so you do the singular value decomposition, and then you can get out these big matrices. But if you look at just the right components of them, this tall and skinny matrix, this small square matrix that only has stuff on the diagonal, and then this long and short matrix. You put them back together again, then it's going to give you this k-dimensional subspace that you wanted. So this is pretty cool. It's all kind of loaded in this operation, which is there's these libraries that are written in like really heavily optimized Fortran that any programming language you use, at least any reasonable one, will have this built in. They all call the same subroutines underneath. And they do this like very accurately, very efficiently. And so usually you call this without thinking about it. If this runtime becomes a problem, we'll talk about some techniques that can deal with that later. But for the most part, you can use this as a black box to call this. Okay, so what is going on here? How does this work? How did I get this k-dimensional subspace here? So let's dive into the linear algebra a little bit more to see what's going on here. Okay, so one important thing about these orthogonal matrices is that let's say that I can write V. Actually, let me add some notation onto here now. These values here, these are going to be called the, it's not a good choice. These SI are going to be called this, these are called so these are called the singular values. Okay, these elements on the diagonal of the S matrix. The rows of V, these are called the right, these are called the right singular vectors. And these columns of U, these are called the left, and these are called the left singular vectors. What's going to happen is, and I'll draw some pictures to help with this. These right singular vectors are going to give us a basis, like a coordinate system that lives in F, this subspace that we found. These singular values are going to tell us how important each of those directions is. And then these are going to map it back onto the individual data points. So these tell us just about kind of properties of the data as a whole. If you think of each of these as data points, they kind of tell you aggregate statistical properties of the data as a whole, and this maps it back onto the individual data points. So they all contribute towards these statistical properties, kind of how I like to think about it. You can do the same thing if you looked at the transpose of A. You can flip this around, and this whole thing is this whole product. Think of D data points in n-dimensional space, and sometimes you want to think of it the other way. So don't, be willing that you can think of them that way as well. Okay, so why does this work? Well, so let's write these right singular vectors, v, as v1, v2, up to vd. Right, so these are the columns of v, or the rows of v transpose. Okay? And so what we're going to be able to do is we're going to say for any vector x that lives in Rd, we can write x equal to the sum of I equals 1 to d of alpha I times vi. Okay? So we can write this vector as the sum of a bunch of these weighted vectors from the right singular values. You can do similar things, transpose with the left singular values with the n-dimensional vector, but okay? And so these alpha i's, it turns out that the alpha I is exactly, turns out it's the dot product of x with vi. So it's just the dot product there. Okay, so I can write this in this coordinate system. Okay, so now if my coordinate system, my right singular vectors, was the original orthogonal coordinate system we started with, the x-axis, the y-axis, and so forth, then what would these vectors look like? Well then, if this was the original coordinate system, then, so if this was the original coordinate system, then, so vi, and actually usually people call that ei, then it's going to look like 0, 0, 0, 1, 0, 0, 0. Right, so this is the ith entry. Okay, so I needed each of these vectors to be have a unit norm. So that means if I summed up all the squared entries, that they would sum up to 1, and so I have only one entry that's 1, so that works. I need them all to be orthogonal with each other, so if I took the dot product, right, with this one and a different one that had a different entry as 1, it's going to be 0. Right, so this works as a coordinate system, and then if I added these up, well, the dot product with any vector, and this just gives me the ith coordinate. And the dot product is this, remember, the sum of, you just sum up the first coordinate with the first coordinate plus the second coordinate, and all of them are 0 except for the ith one. Right, so I get back this vector again, one coordinate at a time. But with the new coordinate system, the same thing works, except these vectors are not like all zeros except for one in it. They're still orthogonal to each other. It still gives me a coordinate system, just a different one. And I can still write my vector x in this way. So this means that it's giving me a new coordinate basis. And so I could think of writing it in this coordinate system instead. I could say that x in this coordinate system is equal to alpha 1, alpha 2, up to alpha d. In this new coordinate system, where I had v1, v2, if I wrote the coordinates in this space, this is slightly rotated from the original coordinate system, well then I would go to here. That gives me the point x, the same way as I did before with the original coordinate system. Let's go through an example of doing this. So this is what allows the right singular vectors to change the coordinate system. And then it turns out, because I only have k of them, I only have k coordinates. So I can only live in a k-dimensional space. Because I stopped only using k, I only have a k-dimensional space. Okay, let's go through an example here. And right, so I've got this example in the notes. Why is it doing that? Okay, so go through a small matrix A, which is going to look like 4, 3, 2, 2, minus 1, minus 3, minus 5, minus 2. And so I've done something so that I've made sure that this was what's called centered. So if I sum up each of the columns, it's going to sum up to 0. That'll make things work a lot nicer. Otherwise, it's going to be a little bit, some things might seem a little bit more strange. Okay, so I'm going to get these different data points, which are roughly, the first one is roughly here, the second one here. It's not a good color. 4, 3 should be 2, 2, then minus 1, minus 5. Wait, minus 1, minus 3, and minus 5, minus 2. Right? So these are the 4 data points here. Okay, and so if I do the SVD and I have it written out in the notes, I'll actually just write out S and V. So S is going to be 8.16, (8.16), 2.3, about 0. So this is going to be the S matrix. The V matrix is going to be minus 0.8 roughly, minus 0.58, minus 0.58, and 0.81. Okay, so each of the columns here, so this is the first right singular vector. And notice that these are zeros, sorry about that. If I sum these up, and if I square these and add them up, it's going to be 1. Same here, and these are orthogonal. If you flip one of the signs, it's going to be, it's going to make those vectors orthogonal. Yeah.
Shouldn't S be squared?
No, S is, I mean, the top part of it is squared. This is not n by k. Remember, if I needed to multiply these together, I needed S to be n by k. Otherwise, the coordinates don't work. But the lower part, I can ignore. Yeah. Otherwise, you can't multiply a d by d by an n by n matrix. So, okay, so, and then you can write out U, it's a 4 by 4 matrix I'm not going to write out. Okay, what's interesting is that the first singular vector is going to be the first column of V. That's going to point roughly to here. Okay, let's draw a line through here. It turns out this line is roughly going to be F. So if I were to project onto F here, this is minimizing the sum of the squared errors. These lines you can't really see. Right, so this choice of F, this first direction, is minimizing some of the squared errors to a one-dimensional subspace. Okay, and if I draw, so this is V1. Switch colors. V1, and then V2 is going to be orthogonal. So this is going to be orthogonal here. This is V2. Okay? And so they should both lie on a, and also see that they both lie on a unit ball. It's going to go around the origin as well. So they're both going to be these unit vectors. So this is the picture. And so if I wanted to write, one of these data points, say the first data point at 4, 3 in these coordinates, I write the dot product with V1 is going to give me a negative value. This would be like -3 or something. And the dot product with V2 is going to give a positive value, like +1. Okay, and so, so when you think about this, one thing that's useful to do is now let's look at some data point x right here. Okay, so let's call this x, and let's look at the process of what ax does. And this is, remember, equal to us v transpose of x. What we'll do is we'll write this out in parts, step by step, and see what happens when I multiply x through by here. Okay? One way of viewing this, afraid of drawing too much on this picture, but let me try doing this. One way of viewing these, well, let me try doing that later. I don't want to screw this up too much. Okay, so so let's look at Vx. What is Vx doing? V transpose x. What this is going to do is it's going to change the coordinate system. So if I look now at, all right. So if I look now at Vx, that's V transpose x. I'm going to call this, to match my notes, we'll call this this xc. That's actually kind of what the Greek letter looks like. It looks like a squiggle. Okay, so what that's going to do is it's going to give, I'm going to draw this in a new coordinate system now. This is V1. This is V2. Okay? And these extend out, right? This is a coordinate system. And and now I can draw and if you remember, X was chosen so it's up here, so it lied on this unit ball. That means that if I draw the same unit ball again here, right, so V1 should have also only gone out to here. So now this point X is going to live, where is this going to live? It's going to live around out here. So this is xc, right? So this is now, it still lives on the unit ball. So it's still a unit vector, but I've written it in this new coordinate system defined by V1 and V2. Okay, so if I go, let's see if I can get these on the same page at once, but if you look at the V1 coordinate, it's going to be it should be negative, right? And that's what I'm seeing here. The V1 coordinate is negative. The V2 coordinate is positive, right? That's what's happening here for X. So I've just done a change of basis here. I've written it in this new coordinate system. Okay? What happens next? Well, the next step is to write out this eta is going to be S times, which is going to be S times V transpose of X. Okay, so what's going to happen when I multiply it by this S matrix now? Turns out it's going to scale this out. So this is where the scaling information of the matrix is all stuck inside of this S matrix. So to draw this properly, I need to draw. So I still have the same coordinate system V2 and V1. But now my unit ball turns out to be scaled. So if I remember, let me draw this more essential here. This is V2 and this is V1. And so if I remember my S matrix, the coordinates are 8 and 2.3. So now this unit ball itself is going to get scaled out. It's going to go out to about 8 and 2. It's going to become this ellipse. Okay, this should be a perfect ellipse. You can't really see it here, but these coordinate axes go out to this ellipse. Let me try. There, now you can kind of see it, right? So this probably can't see on the video though, but there are great pictures in the LaTeX notes. But it's kind of scaled out this unit ball, so it's now skewed. And so this point xc, which used to be on the unit ball, is still going to be on this unit ball, but it now got scaled out to here. So in this new scaled coordinate system, plus the scaling, now this is away from the unit ball, it's on further away. So now its coordinates are going to be something, this is going to be roughly, the v1 coordinate will be something like 7, and the v2 coordinate will be something like 2. Right? So it's no longer a unit vector. And then there's one more step, multiplying by u. This is going to lift it to a 4-dimensional space. It's going to give me 4 coordinates here. And this is going to be a bit confusing because I know any data point I started with must lie in a 2-dimensional space. So it's going to give 4, it's going to change this 2-dimensional coordinate system. It's going to tell me, it's going to give me 4 orthogonal vectors, but they're going to live in a 4-dimensional subspace. So I'm not going to draw a picture for that one, but it's going to look kind of similar. So I think the first two, the right singular vector and the singular values, are important. One is changing the coordinate system, the other one is scaling. Okay, so one thing important to notice here is that any point that lived on a unit ball before must lie on this ellipse. Okay? It must lie on this ellipse here, and an ellipse has a very special structure in that if it lies on the ellipse, there are certain special axes of the ellipse that define it. And these are exactly what the right singular vectors are telling you. They're telling you the axis of this ellipse for the scaling. So if I look at the norm of this red point here, eta, and the norm does not change when I multiply by u. So it turns out that the norm, and this is the 2 norm of eta, is going to be equal to the 2 norm of x, of a times x. So if x is a unit vector, then the 2 norm essentially tells me that there's some ellipse that is describing kind of for any unit vector that the length of that unit vector is going to lie on the ellipse. So if I go back to this picture again, there's some sort of ellipse here, and I'm not going to quite draw it big enough, but it's going to look something like this. Kind of like this. And so any unit vector, I choose x, and I multiply that by a, the norm is going to lie, for a, the norm is going to lie out here. So the length of this vector, so this is going to be ax, is essentially going to lie out here. It's actually going to be a 4-dimensional point, but so the norm of this is going to lie, it's going to describe the direction x to the point on some ellipse. And so the singular value decomposition is very special in that this corresponds with this sort of ellipse. Okay. Okay, so there's probably more information than you strictly needed. I think some of these tidbits are helpful in understanding different aspects of working with the singular value decomposition. Yeah.
Sorry, just one question. I probably missed something, but my understanding of SVD was to go to like a lower dimension, like
correct
complexity.
Yeah.
But you just said that the U maps us like adds 3 dimensions in this case.
That's right. Yeah.
Can you explain like what?
Right. Okay. So it's mapping you to a 4-dimensional space in my example, but all the original vectors x needed to lie in a two-dimensional subspace, so there's some two-dimensional subspace that it lied on in there. So the U matrix is mapping these properties onto the individual data points. So I had 4 data points that I started with, and it maps this kind of the effect of each of the singular values back onto the data points. So
is each of the 4 vectors representing like one of the data points?
correct, yeah. So each of those tells me how much does each data point contribute to each one of those singular values. That's another way of going back the other direction. So the dimensionality reduction aspect is if you took this V matrix and you took just the first column and you just use that. So that's this line F, this subspace running through here. That's how you do the dimensionality reduction. So if you only took, then everything, if you only use the first vector, then everything is going to lie in a one-dimensional space instead of a two-dimensional space. Right? So if you, now I can't draw pictures and illustrate it if I started out with 10 or 100 dimensions, but if I wanted to go down to 2 dimensions, I take the first 2 dimensions, and then I can use this new coordinate space defined by these 2 V1 and V2 vectors to draw all the data points in essentially the best way possible. So that's where you do the dimensionality reduction.
So you basically, after you multiply by the U matrix, you just take, if you want to do one mesh, you just take one of the vectors? Is there a way to know like which vector to choose?
Yeah, so there's in sorted order. So the first singular vector is, let's go up to this picture here. The first singular vector is the top row of V transpose. That's associated with the first singular value, S1. That's the largest singular value. That's the most important one. So they come to you in sorted order. So you want to drop the lower ones. Is there another comment or question?
I don't think so.
Okay. So if questions, comments, please ask them. So
So the rows of V would be the V lines on the subspace of RD.
the
Rows of V, if you're like reducing the dimensionality, would be lines on the subspace that you're mapping onto.
So the columns of V, the rows of V transpose, those define the basis in the
So
new
it actually have to
subspace.
be-
They give you a coordinate basis, so that kind of your new, if you rotate them, then they give you the axes, right?
Okay.
That makes sense? Right, so basically I've taken the data, this example here, I've taken these 4 data points and I could redraw them in this subspace with V1 and V2. Here, I can try and, let me try and do that here.
I understand. You don't.
Well, I think this might be illustrative, right? So this is A1, and if I put it in this new subspace, it's going to be something like A1 here. If I took A2, it's going to be something like A2. If I do something, and then this was A3, and then this is A4, would be here. Something kind of, I might not got them quite right, but I can draw them in this new coordinate system, yeah.
If you tell you can calculate the numbers in the S&P matrices.
Yeah, so you can think of, for the purposes of this class for now, we'll kind of mention how you would do it a little bit later in the PageRank part of class, but you can think of just calling a black box function in MATLAB or someplace else. It will give you these. What?
Some black box function.
Yeah, so there are various ways. We'll talk a little bit about the power method-based ways in the PageRank part of class, but I'm not going to get into those details. Yeah, so think of this as a black box. It's going to do it for you. Yeah. Okay. All right. So, okay. So this is. Let me say one more a few more things about this. Let's see, this best rank K approximation, right? So this is, so let's say I took the top K for, let's say, K equals 2 or 3. In the example, I was using K equals 1 because that's what I could draw. But let's say it was, say, 2 or 3 or 10. What properties does this map have? So this defines this mapping function onto this lower dimensional subspace, right? So now you can kind of see how this subspace F, it lies in RD, but it has these K coordinates, this coordinate system. So you can really think of it as being RK, this K-dimensional Euclidean space. So what properties does it have? It has kind of these two properties. One is that I've mentioned that it's if you want to minimize the sum for all AI and A, so if you want to minimize this, so this is, you can end up writing this as A minus, space here. This is equal to A minus AK. So the Frobenius norm. So what the Frobenius norm of a matrix is just, so if I look at, this is just going to be the sum over all entries squared. Okay, so now AK is also n by d, right? So I have another n by d matrix, so I can subtract it coordinate-wise, A minus AK. That's a subtraction symbol there. And so I get another matrix, A minus AK. And this is kind of, think of the noisy part of the data. And if I sum up and square all of those entries, then that's the same thing as this sum of the squared projections. Okay? So it's minimizing this. If I restrict that this is a k-dimensional subspace, or AK is rank K, then this minimizes this cost. The other thing it does is it minimizes, if I look at A minus AK 2. So this is the spectral norm. So if I look at the spectral norm, this is equal to the max over all x such that it's a unit vector, actually. Well, just it's non-zero, basically. If it's a unit vector, then mx. Right, so if I remember this mx vector, if I remember what this norm, this vector does, I can think of it mapping it to this, onto this ellipse. It's a unit vector, and it points and it hits someplace in the ellipse. And so if I'm minimizing this, it's what's left over after I've taken out the long part of the ellipse. I just have the leftover. So if I picked any one direction that's left over, how large can that be? It turns out this also minimizes this. This is equal to S k plus 1, it turns out. So the k plus 1 entry of S. So if I looked at this guy here, the k plus 1, that's the last leftover piece that's left. So there's a leftover ellipse of all the stuff I didn't take out. And the largest direction there was the k plus 1 entry, and that's the spectral norm, it turns out. And so this process also minimizes that. Okay, so these are kind of, it's optimal in both of these regards. Now this is, we talked about these L1 distances that are more robust outliers. Those are harder to work with in this regards. There's not this SVD function you can call which solves it nicely for you as well. So people usually use these that are minimizing this L2 error, the sum of the squared distances. Right? This is a little strange again. Why am I not minimizing just the sum of the absolute differences? Turns out that's a lot harder to do. Okay. All right, so this is kind of this large linear algebra review of what the SVD is doing. So I have 20 minutes left. What I was planning to do is talk about now how this relates to PCA eigendecomposition and the MDS. And these are kind of fairly simple transformations. But if there are questions about the SVD, please ask those as well about how to use this. We'll see some examples, a little bit of how to use this as well. But you kind of want to do this, think of finding a lower dimensional representation of your data as kind of the main thing. And you do that by mapping into this. So if you want, basically there are two ways of doing that. One is if you want the data points to live in the same coordinate system, so you want to understand what the original coordinates are, then you do this UK, SK, VK. If you don't care about the original coordinate system, you just want to live in a lower dimensional subspace, then you can forget about this guy. Right? You just say, I just want to know what is this new coordinate system and how important it is. Then I just need SK and VK. Okay? Then I can map all the points onto this coordinate space using those by just taking the dot product. Remember, I got the new coordinates by just taking the dot product. Right? This gave me these new coordinates. I just took these right singular vectors. I took whatever my data point was. This could be one of the AIs, and I get the new coordinates. So I can just get the new coordinates that way. If I don't care about the old coordinate system. Okay, so in the homework you'll see some ways of playing with this and seeing somewhat how this works. All right, so let's talk about PCA first. So PCA, or principal component analysis. So PCA is finding kind of a subspace that best fits the data. Okay, that's again a subspace that's minimizing the sum of the squared errors. What I kind of glossed over, so is that the SVD, it minimized this something like A minus AK, for instance, such that this subspace F, which is equal to VK, is kind of equivalent way of thinking about the subspace, includes the origin. So it includes the 0, 0 point. If I went back to this picture, this F needed to go through the origin here. This is the SVD finds the best subspace that's forced to go through the origin. PCA, you might not want to do that. You may have that your coordinate system, original coordinate system looks like this, and your data points look kind of like this. And so now the best subspace that goes through the origin is going to be, this is what's going to be V1 based on the SVD. But that's not really capturing your data very well. What you'd rather do is find a subspace here. I'd rather find that subspace. That does a much better job if I look at this projection. It's much better at capturing the data, this other subspace. Okay, so how would I find, so principal component analysis is to find this subspace that's not restricted to go through the origin. So how would I do that? So it turns out that the subspace found by principal component analysis is always going to go through the mean of the data, the average. And remember, the mean is something I can easily compute. I can do it coordinate-wise. Compute the mean of every coordinate, and that's the point here. And so if I know it must go through there, what I want to do is I want to shift this mean to the origin. And so I also want to shift all these data points by the same vector here. And, and so forth. So that all these data points now lie here, and then I can find the subspace that I know goes through the mean based using the SVD. And then I need to shift it back out by the negative vector of this mean. Okay, now the mean is going to be a data point, but you can think of it as a vector, and then you just subtract it from all the data points. So basically the algorithm is first, so the 1 says first, all right, so find mean of data. Let's call this M. Okay, and then 2, for all AI, shift to AI bar equals AI minus this mean. After I do this, now the mean is at the origin. After this happens. Now I'm going to run SVD of A tilde, because all the data points are shifted to the origin. And this is going to give me my subspace F. And then shift F to F plus M. Shift it back out. Right, so this is step 4. This was, so step 1 was here. Step 2 was doing all the shift. Step 3 was finding the subspace, and step 4 was mapping it back out. Okay, and so it turns out that there's a specific matrix called so this process of subtracting off the mean so this process is called centering. And so there's a centering matrix, which you can write the identity, n by n identity matrix, 1 over n, the all 1 vectors times the all 1 vectors transpose. And so now this, I can write actually that A tilde equals Cn times A. And so this matrix itself is dense, but this operation is sparse, so you can do this very efficiently. Because you don't have to, this becomes an all 1s n by n matrix, which you don't want to actually create, but you can multiply them piecewise using linear operations. So you can actually do this pretty quickly, and then you just call the SVD on this A tilde, right? So you can do this efficiently. So this is principal component analysis. It requires the centering step. Otherwise, you're not going to fit your data very well if it's not centered. And so, in particular, a lot of data sets have things where like all the coordinates are positive. If you know all of your coordinates are positive, it's not going to go through the origin, and you really need to do this. Otherwise, you're going to kind of waste the dimension going out there and summarizing it. Okay. So, especially if you're going down to a small number of dimensions, like 2 or 3, this is really important. Yeah.
So why when you do step number 4, why do you shift F by M rather than like the version of M in the new coordinate space?
Okay, I was being kind of, like if you just care about the coordinate space, then you actually don't need to do this. If you just care about putting it in a new coordinate space, you can stop right here. This tells you the new coordinate space. And that coordinate space is centered around whatever the origin in that coordinate space is. The data will be centered on the origin there. The mean will still be the origin. If you care about actually drawing this subspace along your actual data, you need to shift it back. It's a good question. Okay, let's keep going and get through these eigen decomposition as well. So the eigen decomposition. Okay, so if we remember that for some matrix M, you get an eigenvector if this, so if this is a matrix, in fact, it needs to be a square matrix, and if this is a scalar, so if this is a scalar value, then if you find some vector where if you multiply it by the matrix, you get back a scale value of that vector, then this V is called an eigenvector, and lambda is the eigenvalue. Okay? So how is this related to the SVD? Well, one way of looking at this is, let's start with our n by d matrix A, and let's make it square. If I do A transpose A, okay, so if I do this a d by n matrix by an n by d matrix, and this is going to give me something that's going to be, this is d by d now. This is d by d. And let's see what happens if I multiply it by the right singular vectors v. I can expand this out. The transpose of the square matrix of the diagonal matrix S is still doesn't do anything because it flips things over the diagonal essentially, other than making sure that ignore things about the this is actually S transpose, but this is U S V transpose V. Okay, and now this U transpose U cancels out. Because it's orthogonal, this is the identity matrix. So I can drop this. And I can write, and then I can ignore the zero part of this S matrix, and I can write this as this, and then also the V transpose V, and this also cancels out. So I can write this as Vs squared. So I can then think of this as just the square part of S, the d by d part of S, and I get V, the right singular vectors, times the squared singular values. Okay, and so this is actually, I can write this, because it's S squared is still diagonal, this is S squared V, because that's just a scaling. Actually, I'm not sure that's true. What is, not totally sure that's okay. So you can't do that, but for each individual, what this is saying is if I looked at any individual column of V, then it's going to be orthogonal to the other columns. So each of the right singular vectors Vi, these are going to be the vector of A transpose A. and SI squared, the associated singular value, is going to be equals to the ith eigenvalue of A transpose A. Okay, and you can work out and do a similar thing that A transpose U, this is an n by n matrix now, is equal to US squared. So now the left singular values, or the left singular vectors of U are going to be the eigenvectors of A transpose A. And again, the same squared singular values are again going to be the eigenvalues. Okay? Note, if n is bigger than d, I'm still only going to get, I only have at most d values here. So there's still only going to be d eigenvalues. That's because this is at most rank d, even though it's an n by n matrix. Okay, so these are relationship between eigenvectors and singular vectors and eigenvalues. So you can kind of get between them in this way. So they're really the same structure. How you compute them is going to be very similar as well. Okay. Last thing, talk about in the last few minutes, is MDS. This is multidimensional scaling. And so this is a slightly different problem. The input now is going to be a distance matrix D. And so the entry, so Dij, which is it is going to be equal to some distance for some data point I and some data point J. Right, so I'm given just this set of all these, so think of it as an n by n matrix. This is square, n by n matrix, and it includes all the distances in between points. Is stored in this matrix. Sometimes I'm only given a set of n points in a function to compute the distance. And then I can compute this distance matrix. Sometimes I want to try and skip that step somewhere, right? And I want to think of this, there are ways to do this, to deal with this without the Euclidean distance, but I want to think of this as pi minus pj. So think of this as the Euclidean distance. And now I want to find, if I just have these distances, maybe this is like the Jacquard distance. This is something that is more abstract. I want to somehow embed these into some subspace. So I want to find a low-dimensional subspace to draw these in. So I want to embed these distances into a subspace so the distances are approximately preserved. Now, what I'll talk about is called classical MDS. There are other forms that actually preserve the distances. What this does is it preserves the projection, the same sort of, the error I do by mapping it to the subspace, not the actual difference in the distances. And this is a point that's often misdone in the literature. Okay, so I want to kind of use that. If I look at the matrix A transpose and say these are the original data points, then the entry of this is going to be a matrix M, and Mij is going to be this inner product, in the dot product, Naj. And think of these as they're going to be like the Pi and Pj here, right? And so then what I want to do is somehow convert this into the distance. And so I can write out that Ai minus Aj squared is equal to Ai squared plus Aj squared minus 2Ai minus Aj. So if I have these, I can almost convert into these inner products. Then I can treat the inner products as A transpose, and then I can do the eigendecomposition, take the first 2 or 3 dimensions of that, and use that to draw these points. Okay? But I have this distance, and I want to get this, but I don't necessarily know these. It turns out I've only told you the distances, so I can shift all the data points. I don't change the distance. So what I'm going to do is set A1, I'm going to set this to be 0. Okay, and now I can get that AJ squared is going to be equal to AJ minus AI. So now I can actually solve for AI AJ is going to be equal to 1/2 times AI squared, or minus A1 squared plus AJ squared, AJ minus A1 minus AI minus AJ squared. So after this was an arbitrary choice, and then I can calculate all these inner products, map them into I can then fill up this n by n matrix AA transpose from the d by d matrix, and then I can do the eigendecomposition. And you can just call like this eigs function inside of MATLAB, and it gives you the eigenvectors, which are the singular vectors, and you can use those to map to a low-dimensional subspace. So that's multidimensional scaling. But this is classic multidimensional scaling. It's just doing that. So then do eig of A transpose. And this will give you this mapping, and then take the top K. And this gives you a mapping into RK. Okay. So I've run out of time. There are more details in the notes if you want to look this up. If you have questions about this, we can start the lecture next week, Wednesday, on this if you have more questions. I know I covered a lot of material today. Hopefully some of this was review of linear algebra. But if questions, let's come after class or on Wednesday. Midterm, remember, is next week, Monday. No computing devices at all. No calculators, no computers. You can bring in anything on paper. Okay? All right.